I'm Dr. Tamil Shelvi, Professor, Department of Civil Engineering, Rohini College of Engineering and Technology, Irrigation of the Integration of the Varied Flow. Integration of the varied flow equation. In practice, it is often required to determine the distance up to which the surface profile of the gradually varied flow extends. For instance, if a weir is constructed across a river having a mild slope, then it may be required to estimate the distance on the upstream side up to which the effect of resulting M1 profile exists. In order to solve the problem of this type, it is necessary to integrate the dynamic equation of gradually varied flow. The various methods developed for integrating the varied flow equation may be broadly classified as the step method, the graphical integration method, the direct integration method. So these are all the three methods are using for integration of varied flow equation: the step method, the graphical integration method, the direct integration method. The step method of integration of the entire length of the channel is divided into short reaches, and the computation is carried out step by step from one end of reach to other. So, in the channel reach of length dx, which is sufficiently small so that in this reach the surface profile may be approximately by straight line, equating the total energies at the section 1 and 2 at the either end of the channel reach under consideration. The following expression is obtained. So this is S naught dx plus y1 plus v1 square by 2g is equal to y2 plus v2 square by 2g plus sf into dx. So since E1 is equal to y1 plus v1 square by 2g and E2 is equal to y2 plus v2 square by 2g. Here E1 and E2 the values and of the specific energy at section 1 and 2, and the above expression may be written as S naught into dx plus E1 is equal to E2 plus Sj into dx. Solving the above expression, dx is equal to E2 minus E1 by S naught minus Sj minus delta E by S naught minus Sf. Now the step method of integration based on the computation of length and of the surface profile, various quantities that should be known or discharged. The channel shape, the bottom slope S naught Manning's or Chelsea C, and the depth of flow at one of the section. The procedure for computation is follow. Compute the area of flow section A, vectored perimeter P, and the hydraulic radius R corresponding to the known value of the depth of flow. Compute the mean velocity v square by 2g, the specific energy E, and the energy line slope SF at the channel section where the depth of flow is known. The energy line slope SF may be computed by using either Manning's or Chassis formula. SF is n square v square by r power 4 by 3. SF is v square by c square r. So assume a new depth of flow by another section lying very close to the previous one, and from the assumed depth of flow by compute the various quantities as indicated in step 1 and step 2. The assumed depth will be either more or less than the known depth at control section, depending on whether the surface profile rising or falling from the control section. In order to keep the distance dx between the two adjacent sections, obtain the value of the changes in specific energy from the computed values of the specific energy E1 and E2 at the two adjacent sections.